All right, so I use this whiteboard, so classic. Okay, so we're going to get into the very first thing today, which is I'm just going to do XOR, the XOR operation. Okay, so you guys already know how to do this. It's like a review, but what is XOR? So this, of course, goes back to the truth tables. Okay, so this is XOR. The XOR operation, right? So usually whenever I'm explaining things, I'll be using these ideas of, oh, sorry, I disconnected. Right, so I'll be using bits to do a lot of the motivation for the problem. So XOR is from the truth table. So we have a truth table. And we just have to know the behavior, right? So if we have 0 XOR 0, you get a 0. And then if you have 0, 1, then you get a 1. If you have 1, 0, then you get a 1. And 1, 1, you get a 0. Okay, makes sense? So essentially, that's the operation that you're familiar with. And a lot of the encryption algorithms build on this operation. That's how they actually convert. So here, we could say, for instance, that this is the plain text message. Do you see that? So what is the plain text message? The plain text message is the secret, right? So during the Second World War, the Japanese had a secret code for the attack on Pearl Harbor, right? It was the phrase was climb Mount Nitaka, something like that. And that was a code that they used for the attack, right? So that's essentially the secret message that said start the attack. So that's the plain text message. Of course, you want to send that in an encrypted way in some way. So you're going to need to convert it, jumble it, scramble it, as you usually say when you're encrypting something. So this is the plain text message. So this is the climb Mount Nitaka or something like that. So the message, right? The semantic message. Then this is then the key, essentially. What is the key? Probably a random sequence of bits. Okay. And so what you do then is, so let's call this the key. And now you XOR both of these, right? You do an operation like that, an XOR, and then what do you get over here? You get these values scrambled, and that's called the cipher. Does this make sense, guys? So in its most basic form, yeah, go ahead. The plain text message. The plain text is the secret. Is whatever let's say you're saying, here is my password for my bank account, right? So you want to send that to a relative or something across the insecure internet. You don't want to send that in plain text format. If you say, yeah, if you send that in plain text, it's going to get stolen and then they're going to steal all your money, right? So we call that the plain text. And in its simplest form, this actually kind of works already, right? It's got like one little problem and we can't really, it's got one little problem, so we can't really just do this. We have to have algorithms that use XOR. But if you look, you're already encrypting just by doing this, right? So this sequence of, for a fact, that all the text, all the images in your computer are essentially sequences of zeros and ones, right? So that does, you understand that. So then this is the message. Then we just encrypt it with this sequence of bits, which we call the key, and now we get the cipher. Okay? Now, why does this work? Well, it works because of two reasons, right? Which are what? One, this is a random sequence of bits, right? And second, you're not going to share that with anyone. Do you see what I'm saying? So the key is one of the most the thing that you have to protect. You do not share the key ever. Okay? But that's essentially in its simplest form, this is encryption. You take a message, a sequence of bits, and you XOR it with a random sequence of bits that you keep a secret. We call that the key. And then what you get out here is called the cipher. Does that make sense? Any questions about that? All right, so essentially here, just memorize how to do XOR, this truth table, and then I'll talk about it as we start building more complex algorithms. So this is like the most basic encryption approach. From here, the next one is probably the one-time pad, right? And we'll take a look at some of that logic. All right, so let's just do a couple more examples. So I'll do a more complete example here. All right, so so you guys know how the truth tables work. So now let's do something a little bit more detailed here. So I'm going to have a plain text message. So plain text, this is my message, my secret. Okay. I'm going to have then the key. Okay. And then I'm going to produce my cipher text. So that's the other terminology. Cipher text. Okay, so I'm going to have essentially a bit sequence. So let's go with it's a plain text message. Then I have my key, right? So the key. Okay. And then we know that we usually apply the XOR operation to this. And now we can obtain our cipher text. So that's going to be given the truth table. So 1 and 0 gives you a 1. 0 and 0 gives you 0. 1 and 1 gives you a 0. 1 and 1 gives you a 0, right? 1 and 0 gives you 1. 1 and 0 gives you 1. 0 and 1 gives you 1. And this last one gives you 1. Do you guys see that? And that's it. Pretty straightforward, right? So that's essentially the very first operation that we do. And this operation you'll see in DES, AES, etc. Okay. Now, there's a few things that I did here, a few assumptions. So one of them is that I have a block size of 8 bits, right? You can say that. So that's going to be pretty important. So that's what I was saying before. Let's say we have a message that is longer than 8 bits. Maybe it's like 64 bits, right? Or something like that. And we're using blocks of size 8. Then we're going to split this whole message of 64 bits into blocks of 8 in sequence, right? So we would be like, we'll grab the first 8 bits. That's what the first block. Then the next 8 bits to 16, that's the second block. So these are then plain text 1, plain text 2. Do you see that? Oh yeah, go ahead. That's padding. That's what I was saying about padding. So the last one, so that's a good question. So you're saying like if it's 67, right? Yeah. Yes, exactly. So the last block, So 64, and then after that you have 3 bits, correct? So those 3 bits, that's a good question. So we have the last block, which would be these 3 bits of information, and the rest is padding, which is like adding zeros or spaces or things like that. And actually, we'll cover that in this week's lab, and then later on in Python also. You'll have to implement this. You'll have to take a message, break it into blocks, and then encrypt the whole thing in Python at some point later in the semester with the XOR operation. But I'll give you all that code. Any questions? All right. So yeah, so that's the very first idea. It's XOR. So a few tricks. What if you have this? So let's say you're an attacker. Let's just kind of motivate some of this. So the attacker, right? So we have an attacker. Okay. And the attacker is listening. So you're going to have point A, point B, right? And the message is being sent over something like the internet. So the assumption is that while in transit, the attacker is trying to steal your information because it's really valuable for whatever reason, right? So what's being sent across the internet? Let's say this is like the North Pole and this is the South Pole. So obviously it's being sent a long way, right? So what's being sent? So the thing that you don't want to send the plain text, right? You want to send the information, but not the plain text. Instead, what you want to send is the cipher. Do you guys see that? So that's what's going to get sent. So essentially, this block, which is a sequence of bits 1 0 0 0 1 1 1 1, is being sent. But the attacker, Zelda, or call it whatever you want. I usually call the attacker Zelda. So she's going to be listening, grabs the message, but she can't really understand what it means, right? What does she need? The key, exactly. She needs to know the key. So if she has the key, so who has the key, presumably? So it's going to be if A and B are talking to each other, and this is Bob and Alice, right? Bob and Alice, then you assume that they both have the key because obviously they need it to talk to each other, right? So to decrypt the message and obtain the plain text, Alice will then take the cipher that she receives, 1 0 0 1 1 1 1, and she's going to take the key that she has, which is 0 0 1 1 0 0 1 0, right? And now you proceed, you apply XOR, and it's very simple. Obviously, this assumes that they used XOR on the other end. If you use another algorithm, you will not be able to decrypt it, right? So you have to agree on the algorithm. So now we apply XOR again, and let's see what we get. So we know that 1 0 gives you 1, 0 0 gives you 0, 1 1, right? 0 1. Does that match the original? Yes. Right? Do you see that? That's the very basic idea with encryption. Pretty simple, right? Pretty straightforward. So from here, we'll be doing this quite a bit, but we just start adding complexity, right? So messages are going to be longer. The blocks are going to be longer, right? Obviously, now there's another concept here that's pretty important. In this case, this is the whole message, but you can't really encrypt the whole message with one key of the same length as the whole. So here we have a key that is the same length as the message, right? So that wouldn't be practical because if you were encrypting that 3-hour movie, F1, that would be a very long key, right? So that wouldn't be practical. So instead, and for other security reasons that we will discuss later, like the one-time pad, we have to break it into blocks, and the key could be of the same size as the block, or you'll need to, maybe the key is a bit longer, but you need a mapping function that makes this to be the same size as the block. Do you guys see that? Any questions? All right. So that was XOR. So are there any questions about XOR? Is that clear? And I assume we can move on this one. All right. So that was XOR, the most basic and underlying, one of the most basic and underlying operations, at least for block ciphers and symmetric encryption. Let's see. All right, so then I've introduced Bob and Alice, and I'll just start introducing now some of the formal ways of describing cryptography. Some of the ways that we can represent it. Okay. Let's see. All right, so let's kind of do this. So I usually like to start here. So this is the beginning, right? So we have something called SSL. And this is the way that we can achieve a lot of the principles. So this stands for Secure Socket Layer. There's a protocol in the network called TLS. And what you have to understand is like this is like the set of algorithms, right? And this is just the formalization of those algorithms into a protocol, right? That works for the internet called TLS, okay? Transport layer security. I believe it stands for TLS stands for transport layer security, but essentially it's just a network protocol that implements SSL. Does that make sense? So when you use SSL, so when you want to have a secure communication between Bob and Alice over the insecure internet. So for instance, you have a laptop, and then you have a server, right? So the classic client-server architecture. We have a server. So it's just some communication between two parties. So, you know, e-commerce, right? We all know about e-commerce, Amazon, etc. So that's a classic example. So what we want to use is this SSL TLS. Why do we want to use that? Because that's going to give us all the pillars, right? So it's going to give us confidentiality, integrity, authentication, non-repudiation. So it gives us all of those things. All right. So we are going to make this communication via SSL and TLS between two parties, which again, Alice and Bob. So we use Alice and Bob because a lot of the time we need to know in the communication, are you Bob? You know, who is receiving, who is sending? So this is a common practice in cryptography to just use these people, Alice and Bob. All right, so we want to encrypt our data. We want to use SSL and TLS. So we want to achieve confidentiality, integrity, and availability. But pretty much the entire class will focus on the primitives, all the blocks that you use to create SSL. Okay, so SSL is made up of asymmetric encryption, symmetric encryption, hash functions, and those concepts. Okay, so I can't really give you a definition of SSL that you will understand right now, but later in the semester, I will. Okay, does that make sense? So that's kind of how I'm motivating this. So we'll understand it better later on because there's several problems that we have to address, right? One of the problems you already saw. So I can go back to one of the slides. So in here, for instance, I was sending this cipher between Bob, you know, we have Bob and Alice, right? So we send the message. So Bob encrypts and Alice decrypts. But for Alice to decrypt, she has to have the key, right? She can't without it. But then we have a problem. We know how to send the cipher, but then how do we send the key? Do you see what I'm saying? Because the key is essential, right? Whoever has the key can decrypt the message. So we need to have a way to not only encrypt and send the cipher, but also a secure way of exchanging the key, which has to be in plain text. Right? Do you guys see that? So that's, these are problems that we need to address. Okay. So we'll see that later in the semester. And SSL uses several techniques to achieve it. All right. So now let's formally define symmetric encryption. Okay. So that's the next step. We're going to formally define symmetric encryption. So I'm going to do that. So the first building block, the first crypto primitive, right? Symmetric encryption. Encryption. Okay. All right. So yeah, and I think we'll stop here for today. So this is the last concept, but it's a good stopping point. So symmetric encryption. Let's formally define it. So we're going to do a diagram first. Here I have E, because we're going to use these parameters. So I have a message M. Okay, that's when I use the letter M, that means usually the plain text message. Okay. E means the encryption algorithm that we're going to have. Here we're talking about Alice. And we have, of course, the key, which is K. Okay. So then we send this over the insecure internet. We always assume the medium is insecure. We don't rely on the medium, right? We rely on cryptography. So E is the encryption algorithm. The encryption algorithm takes K and M to produce the cipher. So in its simplest form, the encryption algorithm could be just XOR, right? That's what you guys know so far. I apply XOR between the key and the message, and boom, I get the cipher C. This is C. All right, so this is send then to the other party, which is going to be Bob, right? Bob. So you have a decryption algorithm, usually the reverse process, which I've already shown that works with XOR. So, but you need to have the same key, right? So the same agreed upon key, which has to be exchanged securely. And then given this, you're going to have then for D, the decryption algorithm will take the key, the cipher, and produces the plain text message M. Okay? So this is kind of the diagram of symmetric encryption and how it works. Okay? So the key here, key is the secret key. Define it as the secret key. And this, usually we're going to think of in terms of length. This is really important because essentially, we determine security by the length of the key. Do you see what I'm saying? Like if I use a key that is like 4 bits, it's really insecure because, a brute force attack or something like that, different techniques that are available could break the message. You just try different combinations, right? So if I'm using a key that's just got 4 bits, I just try all the possible combinations until I figure it out, right? So yeah, the longer it is, this is called permutations, right? So it takes more permutations to try all the possible keys in the space. Do you see what I'm saying? So it's really important. So the secret key, we're going to define it as having a specific size, such as 128 bits or something like that. Later in the semester, we will do examples with RSA, etc., and you will try different key sizes. Okay, and you will see that once you start incrementing the size of that key, the encryption process slows down. Right, so it might take, if again that movie might take too long to download. All right. or to decrypt, sorry. All right, so a few things to wrap up that are really important that might be surprising to you. So number one, the encryption algorithms which in this case are D and E, right? You guys agree, right? We've defined that D and E are the encryption algorithms. XOR right now, but they can get more complicated than XOR. So these encryption algorithms are publicly known. So these algorithms are publicly known. And in fact, that is desirable. The reason is because you want people to test these algorithms, to try to break them, right? So there used to be competitions every year, the RSA challenge or competition, and teams from all over the world would just show up to try to break RSA, right? And so the goal is to test that algorithm to make sure that it is secure, in fact. So usually the encryption algorithms are known, there's no obscurity. So most of the security comes from keeping the key secret, right? So you're assured in a way that if you're using this algorithm with a key of a certain length, all your data is safe. Do you guys see that? So you rely on that. Here we've defined E as the encryption algorithm, D is the decryption algorithm. And then, as I said, the only secret that you need to keep, so the only secret is the key. That one you definitely do not want to share, and you just keep it in your system. So the only secret is the key K. All right, so essentially that's symmetric encryption. So you can see all the parameters. You have E and D, which can be any algorithm that you want, XORing many times. You know, think of like I XOR and then I XOR again, XOR, you know, that's an algorithm. You have a plain text message in a cipher, and then you have the key. So the encryption algorithms, D and E, are publicly known, and that's a desirable feature, and the only secret is the key K. All right? All right, so I think that's a good stopping point for today. Please remember, try to set up the seed VM for Thursday. On Thursday, I will mainly go over the VM and start on the first assignment or lab. So we'll start encrypting some things, an image, some text, and then, of course, we'll continue with the algorithms and the definitions in upcoming classes. Oh, also, yeah, great. Thank you. Did everyone sign in? I have to do the initial course participation, so make sure to sign in. All right, guys, I'll see you Thursday. In the first 3 weeks, you have to do it.